Let's take a look at the physics of capacitors and capacitance.
Let's suppose we have a standard household battery. It's 1.5 volts, 1.5 joules per coulomb. We want to think of that voltage as being electrical pressure. It's capable of pushing electrons around a circuit. Now if we kind of extend our terminals, and we'll put a plate on each one of those extensions, just a metal plate, then because the plates aren't connected, of course you're not going to get a permanent current, but you're going to get a little transient current. And it's going to push some electrons down onto this plate. Of course, the electrons repel each other, so they kind of push back. So you can't get the electrons too close together. There's kind of an equilibrium situation between that electrical pressure pushing the electrons forward and the electrons repelling each other. And let's suppose the charge that develops on that plate is negative Q. Now, from the other plate, of course, electrons would be pulled off. The electrical pressure is kind of a suction. And so you're going to end up with a positive charge, and it would be equal in size to the negative charge on the other plate. And now let's suppose we have another battery, a bigger battery, but really by bigger I mean a higher voltage battery. Let's make it 3 volts. So it's got twice the voltage, twice the electrical pressure. And we're going to extend each of the terminals and put a plate. And then because we've got twice as much electrical pressure, we're really expecting to have twice as much charge develop on the plate and twice as much positive charge on this plate. So we'd end up with a positive 2Q here and negative 2Q here. So whenever we increase that electrical pressure, increase the voltage, we get proportionally more charge on these plates. So we see that one way to increase the amount of charge on the plates would be to increase the voltage of the battery. But there's other ways to do it. Here's situation 1, and here's situation 2. If I keep the battery the same, say 1.5 volts, 1.5 volts, but I change the area of the plates, we've got the same pressure pushing those electrons together. So they should get equally close together in either case. But because you've got a larger area in the second case, you're going to get more charge. So if, let's say, this has an area A and this has an area 2A, then we'd expect that this would have a charge of negative Q, and this would get a charge of negative 2Q. So we got equal electrical pressure pushing those electrons together, and on either plate the electrons should get just as close together. But on the bigger plate, you can get more electrons there because you have more area. And it would apply the same on the top as well. So we can increase that charge on the plates by increasing the voltage of the battery or increasing the area of the plates. Here's a third method. We could take our plates and place them close together. Once again, that electrical pressure will push the negative charges to one plate and pull off negative charges from the other plate. But what is new now is that the positive charge on the top is going to attract more electrons onto that bottom plate. So it's going to kind of act like a suction. And in that way it's going to add to the pressure pushing electrons onto this plate here. So if we can decrease this distance here, decrease that distance between the plates, that should result in more charge. So we have 3 methods so far for increasing the charge on the plates. Here's a 4th method. Once again, we're going to start the same way, and we're just going to put our plates close together. But this time what we're going to do is put kind of a special, it's not very special, but we'll put a material between those plates. Usually we call that material a dielectric. And all that's happening here is that, of course, molecules have electrons inside of them that can move around. And so the molecules get polarized. So if this is the negative plate here, the electrons in the molecule of the dielectric get pushed to the other side, and you end up with a positive charge on this side of the molecule. So we end up with a polarized molecule. And the same thing on the other plate. This is our positive plate. Then the electrons in that molecule will get pulled over to the positive plate. And now you can see you have this layer of polarized molecules with the positive side closer to the negative plate. And what that's going to do is attract more electrons. So you'll get more electrons coming to this plate because they're attracted to the polarized molecules. So now we've got 4 different methods to increase the charge on the plate. We can increase the voltage, we can increase the area, we can decrease the distance between the plates, or we can put a dielectric in between the plates.
Hey, do you want to play a game now? Okay, here, I help. One of these things is not like the other things. One of these things just doesn't belong. Can you guess which thing is not like the other thing? Before I finish my song. Now look closely. Look. Now something here, one of these things does not belong. Now I'll give you a hint. It has to do with how many cookies are on each plate. Okay? You ready? No? Okay, keep looking. I look too. This is hard even for a monster. Keep looking. Oh, did you guess? Oh, yeah? Did you guess which thing is not like the other things? Did you guess with all your might? If you guessed that this thing is not like the other things, you know what? You know what? You're right. Oh, you're absolutely right. You're so smart.
So hopefully you were not misled by Cookie Monster suggesting that the correct answer had to do with the number of cookies on the plate. And you said that the voltage was the odd man out. And that's because the voltage had everything to do with the battery. Whereas the other 3 quantities, the area, the dielectric material, and the distance between the plates, they all had to do with that external configuration. And we call that external configuration the capacitor. So in our case, we had a parallel plate capacitor, but probably the most common type of capacitor is a cylindrical capacitor. And this leads to 2 important equations. One is kind of a definition of capacitance. It's the amount of charge stored per unit volt applied. So if we're going to compare capacitances fairly, we've got to do it at the same voltage. So we want to make it per unit volt. A second important equation is the capacitance of a parallel plate capacitor. And it's given by K times epsilon 0 times the area of those parallel plates divided by the distance between the plates. This epsilon 0 here, it has a value of 8.854 times 10 to the minus 12 farads per meter. So it's just a constant, and that constant is called the permittivity of free space. This K here is sometimes called the dielectric constant, or the relative permittivity of our dielectric material. So for instance, if we've got air or a vacuum inside of our parallel plates, the K value would be 1, and we would really just be using the permittivity of free space here. But you can look up these K values. Sometimes a K value will be as big as 80, which would mean that the electric field is going to be 80 times as strong, basically, in that material than it would be if you just had a vacuum or air between the plates. And it also means your parallel plate capacitors are going to hold 80 times as much charge for the same voltage. Let's get a little bit of practice using those equations, Pause the video, try this question, come back for the answer. Part A, for a parallel plate capacitor, that capacitance is given by the dielectric constant times the permittivity of free space times the area of the plates divided by the distance between the plates. So this is porcelain. So we have a dielectric constant of 6, permittivity of free space just a constant 8.85 times 10 to the minus 12. Area of the plates, be a little bit careful, we've got to use SI units here. So it's 0.5 centimeters squared, and then let's convert centimeters squared to meters squared. And there's 100 centimeters equals 1 meter. So 100 squared centimeters will equal 1 meter squared. So that's 100 squared all over 1. Distance between the plates, once again, you've got to use SI units. So that's 0.2 times 10 to the minus 3. Work that out. You should get 1.3 times 10 to the minus 11. And the units there are going to be farads. Farads are really coulombs per volt. So a farad, and a farad is a humongous amount of capacitance. So what we'd usually do here is write this as 13 times 10 to the minus 12 farads, and times 10 to the minus 12 is what we call a pico. So this is 13 picofarads. So typically for capacitances, we'd be talking about values in micro, nano, or picofarads. In part B here, we're just using the definition of capacitance. It's the amount of charge per unit voltage. So our charge would be equal to the capacitance times the voltage. Our capacitance was this 13 picofarads, or 13 times 10 to the minus 12. And our voltage was 5. So we end up with a value there of 6.5 times 10 to the minus 11 coulombs, or 65 picocoulombs. But remember, a coulomb is a huge amount of charge. A coulomb is a billion excess electrons. So typical charges that we talk about every day are of the order of picofarads and even smaller. Not so long ago, we talked about equivalent resistance, and we said we could take a whole network of resistors and replace them by a single resistor such that we would get exactly the same current coming out of the battery. And we had formulas for this. We had a formula in series, and we said that the equivalent resistance would just equal the sum of those resistors in series. And we had one for parallel, and we dealt with reciprocals for that equation. 1 over R1 plus 1 over R2 plus 1 over R3, etc. Well, in the same way that we will build together a network of resistors, sometimes we build together a network of capacitors. Sometimes we do this because we need a certain capacitance, but we don't have any capacitors that are that size. So by combining them in series and parallel, we can get the overall capacitance that we want. The nice thing here is that the mathematics is going to be the same. We're going to basically get the same equations for equivalent resistance as equivalent capacitance. The only difference is series and parallel get interchanged here. So the series equation for capacitors involves the reciprocals. So the series equation for capacitors involves the reciprocals. 1 over C1 plus 1 over C2 plus 1 over C3, etc. And it's the parallel equation that's easier mathematically because the equivalent capacitance will simply equal the sum of those capacitors that are placed in parallel. So if you are comfortable with equivalent resistance, you're going to be equally comfortable with equivalent capacitance. I could do a formal proof for these equivalent capacitance equations, but I don't think it's necessary. I'm just going to give a brief physical explanation for them. Let's say that we've got a single parallel plate capacitor connected to a battery. Then, of course, the plates have a certain area. Now if I add another set of parallel plate capacitors, if I think of this as kind of one parallel plate capacitor, what I'm really doing is just adding more area. It wouldn't make any difference if I in fact joined these plates together. So in parallel, because we're adding area, we're adding capacitance. So we're effectively adding area, so we add capacitance. In series, let's take these parallel plate capacitors in series. This conductor here, doesn't matter how long or short you draw it. I could effectively take that out of the picture. So if I've got a D1 here and say a D2, and I shrunk this conductor down to 0, my capacitor would look like this. But this piece of metal in the center, it's not attached to any battery, so it's really not doing anything. It's just a thin sheet of something in the middle. And so it doesn't really do anything. So what we really got here is two plates separated by a distance d1 plus d2. So effectively here, when we add in series, we're just increasing the distance between the plates. And then because capacitance varies inversely with distance, we get that reciprocal relationship where when you add more and more capacitors in series, you get a smaller and smaller capacitance. Okay, one quick example. Let's see if you can calculate equivalent capacitance in the same way that you used to calculate equivalent resistance. So pause the video, try the question, come back for the answer. First step, we want to look for capacitors that are either directly in series or directly in parallel. And these two here are directly in parallel. That means we can use our parallel formula. Our parallel formula was simply to add the two. So remember, it's parallel that's easy to do when you've got capacitance. So our circuit can be simplified to this circuit here. There's the original 4 microfarad resistor. And then a 1 and a 2 in parallel will make a 3 microfarad capacitor. Now we've got 2 in series. We need to use our reciprocal formula. So 1 over the equivalent capacitance of our network there will equal 1 over 3 plus 1 over 4. Get a common denominator. You should get that the equivalent capacitance is going to equal to 12 divided by 7, which is approximately 1.7 microfarads. So this network can be replaced by a 1.7 microfarad capacitance such that the same voltage would produce the same charge. One final but very important concept. We would of course like to know what is the energy stored on a capacitor. And the IB data booklet does give us a formula for that. The energy stored on a capacitor is equal to 1/2 times the capacitance times the voltage across that capacitor squared. And I'm not going to give a formal proof of that, but I will give a physical explanation. So let's imagine we've got our battery. We'll have a switch, and we've got our capacitor. Very simple circuit. Then the energy stored, E, should be equal to the work done to move the charge onto the capacitor. And that should equal to the amount of charge that gets moved times the voltage of the capacitor. But we've got to be a little bit careful because that voltage of the capacitor increases. If there's no charge on the capacitor, there's no voltage across the capacitor. So the charge, as we throw that switch, grows from 0 coulombs to Q coulombs. And as that happens, the voltage across the capacitor grows from 0 volts to the voltage of the battery. This V being the voltage of the battery as compared to VC, the voltage of the capacitor. They're not the same until the capacitor is fully charged. Now, if we make kind of a simple assumption here, and we say that VC grows from 0 to V as the charge grows from 0 to Q. And if it does so in a linear manner, then the average capacitor voltage would be equal to the battery voltage divided by 2. So now we can do something up here with this equation. Well, all the charge gets moved, that's the Q. But this capacitor voltage, we want to use the average value for that. So that's going to be the battery voltage divided by 2. And then to finish this off, of course, C is equal to Q divided by V. So I can replace Q by C times V. And I'm going to get C times V over 2, or 1/2 CV squared. There is the energy stored in a capacitor that's got a final voltage V across it.
Okay, we have a question on the energy stored in a capacitor. Pause the video, try the question, come back for the answer. So in part A, we know that capacitor A is 12 microfarads. And we also know the charge on that capacitor. It's 24 microcoulombs. Now, I like to remember that the energy stored in a capacitor is equal to 1/2 the voltage times the charge. And the reason for that is because I just kind of remember the units there. A volt is a joule per coulomb. Multiply that by a coulomb, and you're going to get joules of energy. Now, if I combine that equation with the definition of capacitance being equal to Q over V, then I can rewrite this expression in terms of C's and V's, or C's and Q's. So for instance, I can replace a V here by Q over C, and I'd get 1/2 Q squared over C. Or likewise, I could replace the Q here by C times V, and I'd get 1/2 times C times V squared. So in this particular instance, I have got the C and the Q, so I'm going to want to use this expression here. So let's just plug in. 1/2 Q was 24 times 10 to the minus 6 coulombs. That gets squared, and divide by a capacitance of 12 times 10 to the minus 6 farads. And this will give you an answer in joules. And you should get a result of 24 times 10 to the minus 6 joules, or you'd probably write that as 2.4 times 10 to the minus 5 joules. In part B, that charge of 24 microcoulombs is going to have to split itself over the two capacitors. So we could say that QA plus QB has to add up to 24 microcoulombs. We also know that those two capacitors will be at the same voltage because they're connected in parallel. So we can also say that the charge stored on a capacitor is going to be proportional to the capacitance if V is the same. Really just using this equation here. And the V has to be the same because our capacitors are in parallel. And being as B had a capacitance of 8 microfarads, 12 is 1.5 times as big as 8, therefore QA must be 1.5 times as big as QB. So now we can make a substitution, and where we see a QA, we can plug in 1.5 QB. And we'll get that 1.5 QB plus another QB should be equal to 24. And if you work that out, you'll get that QB is equal to 24 over 2.5, or 9.6, and that would be in microcoulombs. And I'm running out of space, but QA from this expression has to equal 1.5 times QB, which is 9.6. So we're going to get QB equal to 14.4 microcoulombs. So there's the answer to part B. In part C, we're asked for the total energy stored on the two capacitors. And we know the capacitance of each of the capacitors. We also know the charge on each. QA was equal to 14.4 microcoulombs. QB was equal to 9.6 microcoulombs. So when we add up 14.4 and 9.6, we get that 24 microcoulombs back. So we can add up the energy stored on each capacitor individually. We're going to use the expression 1/2 Q squared over C, because we know the Q's and the C's, one for A, one for B. Plug the values in, and you should get a total energy stored of 14.4 times 10 to the minus 6 joules. Or we'd usually write that as 1.4 to two significant figures times 10 to the minus 5 joules. So that would be the total energy stored on the two capacitors.
Let's summarize the big ideas from the video. We started out with the definition of capacitance. And here's the equation for that from the data booklet. Capacitance is equal to the amount of charge stored per unit voltage. 2, we looked at the case of a parallel plate capacitor, and we had a formula for that. Here's the formula as written in the data booklet. Notice here that they write this relative permittivity epsilon. That's going to equal the dielectric constant times the permittivity of free space, which has a value of 8.85 times 10 to the minus 12. Thirdly, we talked about series and parallel combinations of capacitors. And here's the formulas as written in the data booklet. Remember, it's going to be just like equivalent resistance, except the formulas for parallel and series are kind of reversed. And fourthly, we talked about the energy stored in a capacitor. And we said that was given by 1/2 times the capacitance times the voltage across the capacitor squared.
So please take the time to like videos, to make comments, to ask questions, become a subscriber, sign up for notifications, become a member or a Patreon.
And that's all for today, folks. Thank you very much.